All right, I've already gotten going on this problem. And what I did, which I always recommend when you're dealing with something that looks like it should be graphed, is I went ahead and graphed it. I plotted these x and y points. Remember, f of x, that's y. I plotted these x and y points over here on this graph. And what I think that's going to do for us is it's going to make it really clear what the problem is and what's preventing the inverse of f from being a function. So remember what f is. F is a line. Usually, in this case, it's called a dot function. It's actually not the line connecting these. You might think, oh, this is f. It's something that looks like that. Well, yeah, normally it would be, but in this case, it's just a dot function. F is a series of dots, and f does not exist in between. There's no f in here, right? That's just blank space. So the only thing that would prevent f itself from being a function, f of x, is what I'm talking about. The only thing that would prevent that is a vertical line which went through and hit more than one dot at once. And see, all these vertical lines I'm drawing only hit one dot at most because the dots are not vertical. Well, great, that means f is a function. But what I'm talking about in this problem is the inverse of f of x. And for this, we need to use not the vertical line test, but the horizontal line test. And I've written that down here. Remember what the horizontal line test says. If there's no horizontal line which touches f in more than one place, then the inverse of f is a function. So let's start drawing horizontal lines. Here's one. That only hit the function in one place, right at this dot over here. And because it only hit once, it's fine. The inverse of f is a function. This one, no problem. This one, uh-oh, look at that. I just hit two dots at once. That means it turns out the inverse of f is not a function. Are there any other trouble spots? This one's okay. This one's a problem right there. So let's just focus on those problem ones. Those two lines right there. If it weren't for those two lines that hit two dots at once, then the inverse of f would be a function. That's what we want. So here's the question. What do we have to limit the domain to? How do we limit the domain of f to create an inverse which is a function? And limiting the domain is very easy. What it means is you're getting rid of a dot like that. Okay, so in other words, which dots have to go? That's the question. And here we are. This is the situation. One of these has to go, and one of these has to go. If one of each of those pairs of dots goes, then we don't have any horizontal lines that are problems, and our inverse is fine. It becomes a function. So you're looking for something over here, which basically says that. You're looking for a set on the left, which has one of each of these pairs eliminated. So let's go through these sets one at a time. I'm looking at this one right now, top one. Look at that. Dots at x equals 3 and x equals 4 are in this one. So that means the horizontal line is going to run into a problem. This is not what we're looking for. Okay, so that's not it. In the second one, oh, look at that. Those dots are still there. This one's not it. Okay. In numbers 3, 4, and 5, there's no, see in here, I don't have dots at x equals 3 and x equals 4. That makes me pretty happy. But I'll bet I still have some dots at x equals 1 and x equals 7, because those were two of my other problems, right here and right here. So there it is. 1 and 7. That's not an inverse. The inverse is not a function. 1 and 7 right here. No, the inverse is not a function. There's only one. There's only one of these, which if I plotted it out, would not contain a horizontal line hitting two dots. And therefore, this is my answer. That's what I have to limit the domain to create a function out of the inverse of f.